And we're talking about generative bamboo. I'll turn it over to you.
Thanks a lot. So I'm happy to be here today to talk about our research. I co-lead the BioDesign research group, and my focus is mostly bamboo and a few other materials. So in that group is Kay Edge, Stefan Au, Brooke Kennedy, and Dan Heineman and Jennifer Russell collaborate from SBio. Also, the work is already kind of mapping a bit around the world. These little dots represent people that we're already in talks with or already collaborating with. A lot of this work, its biggest impact, if it works, will be on the parts of the world in the tropical zones where we expect the most construction to happen between now and 2050. So why would that be important? Along with carbon sequestration and some other things, we just think about the amount of time it takes for materials to generate. This gives you a sense for scale. The leading materials in the built environment are concrete and steel. Obviously, they take quite a long time for the minerals to develop to make the rocks that those things eventually come from. But even compared to trees, bamboo is incredibly fast growing. So, we're exploring the intersection of technology using generative design tools, using computation, and using both analog and digital fabrication tools with biomaterials. Bamboo is the sort of main momentary focus, but I try to make it very clear that I'm not a bamboo expert. I'm really a craftsman with some expertise at the intersection of design and technology. Bamboo is just a fascinating problem to solve and has great promise if we can solve the problems of making it more appetizing, should I say, for the built environment. Even in maybe non-Western countries or less developed countries, there's still a very Western expectation for how the built environment should be for first world life. So, these goals, we hit many of these UN goals for sustainability, but I think probably the most important two are the sustainable cities one and this idea of responsible consumption. So we're interested in this notion of life-centered design. This is where, unlike a kind of purely human-centered model, we don't put humans in the middle. We're just part of a kind of system, hopefully a biological system. So why bamboo is so interesting to me. First, it's a farm product. Second, it's regenerative. It grows from a rhizome, which is a pretty unique characteristic of only a few other kind of materials. As I've already said, it grows incredibly quickly. And then the last thing is nature has engineered an incredible structure. And that's really kind of a fascinating place to start with the material, is that by itself, as it grows, nature has made it resilient to the wind. And it grows in these roughly 60 to 100-year cycles. So the rhizome always regenerates after about 100 years. It'll massively seed, and the whole entire species on the planet over about 20 years will die, and then will regenerate again. And so for these reasons, we find bamboo a really promising opportunity. So we're interested in also thinking about what might normally with food be farm to table. We talk about farm to classroom. So really understanding the whole chain. I've spent some time in Latin America and some time in Asia looking at bamboo, and particularly in Vietnam and Bali. And basically you harvest 1/3 of the bamboo once you have a mature grove every year. It gets heated over a fire and bent straight because it's not particularly straight. Then it gets treated with boric detergents and acids to drive sugars out of it. Then eventually it's sun-dried, and then in our case, it's packed into a container, shipped to us. And this is where we kind of learn a big lesson, which is this is where I discovered we should think from farm to table. It shows up to our door completely full of mold. And that's because coming from Asia, it literally rains in the container. And so as that rain, happens continuously, and it's very hot, and there's all this kind of these spores of mold, the mold kind of prospers. So we started by cleaning all the bamboo, stick by stick in the lab. At first, that was just a kind of penance for not thinking so hard about the full kind of cycle. But then I came to realize that we actually got to know the bamboo in a very different way by touching it. And so now that's kind of a ritual that everyone in the lab goes through when they start engaging in the work. And eventually we fabricate with it. So a few other interesting parts just about bamboo. There are over 1,000 species. If you look at the figure on the far left bottom corner, the difference in wall thicknesses is quite interesting. Some are very thick-walled, some are very thin. The image second to the far right, showing these different species at different diameters. That's not one pole, but that's many species. So there's huge ranges of what bamboo might mean. Commonly, the wall thickness is like the third image from the right, which is Madaki bamboo. And what we are interested in is these more solid species, like the figure in the far left, bottom left corner. So we've been thinking a lot about how you might build with bamboo and what the precedents of the past are, and even the current ones. And we find this kind of hole. People talk about bamboo engineering and engineering bamboo. On the one end, you have pole construction, and the other end, you have composites. And what we're interested in thinking about is that there's this big space in between that's very unexplored right now. And so we're interested in what we would call slightly or lightly modified bamboo. So just to give you a sense of the taxonomy of one of the poles of the species we're working with, they're really, really solid. I did the calculation. I didn't believe it the other day. 94% for one of the species. So it's a hollow material, but it's 94% solid by area. And that's kind of hard to imagine. When you imagine a bamboo pole, just by calling it a pole, you assume kind of a hollow quality. And it really is this material that sits in between solid and hollow. So the image in the middle there is us just sawing a short section of it into a square section. That you couldn't do in most pipes or tubes. On the far left, that's where the calculation for 94% solid came from. We looked at each of those cross sections. We took an area. Then we subtracted the hole in the middle. And then the far right, what's pretty interesting, which Dr. Hyman helped us discover, is that this species, which is called Dendrocalamus strictus, or also known as Calcutta bamboo or iron bamboo, it's as it's as strong as a 2x4 bending the hard way. So it's half the height, roughly half the area, and in terms of its bending strength, it's comparable. Otherwise said, maybe it's twice as strong. And also, this species grows in 3 years. That 2x4 took at least 20 years to grow. So we have two main projects. One we call retooling bamboo. The other we call smart cross-laminated bamboo. And we're moving to maybe smart bamboo or mass bamboo as we realize that it's more than just a panel system. So one of the things we do first, I mentioned how we touch the bamboo and clean it. That's one way of trying to sense or know the material kinesthetically, but we're also trying to do it with technology. So taking photographs of the bamboo, turning those into scans, finding edges, using hardware and software. And so our goal is to really know the material in every way that we can so that we can make the most out of every piece. So generally speaking, since the Industrial Revolution, we try to kind of standardize materials. Our goal is to actually work with the eccentricities of material to kind of bring or eke more out of them. Ben encouraged me to grow bamboo when I gave him a metaphor a few years ago. And so on the left here, a small mini seed grant, we grew bamboo trying to determine whether or not we could impact its longitudinal growth by its orientation with light. And it worked, but I also learned how impractical it was. But in many ways, it's important in our lab to be taking risks like that, doing things that are unconventional, that most people that know about bamboo would tell you are crazy. And some of them turn out to be crazy. Others become new inventions. On the right is the first CNC machine we built. That's a shop in Vietnam. He's an expat named James Wolf who builds bikes and furniture. And we took a machine there to test and see if we could understand better how bamboo could be fabricated with technology. So tool making is a huge part of what we do. I'm actually trained as a metalsmith. That's my graduate degree. And I was really a blacksmith. And so I've always been interested in tool making. And the tools we make now, they span from the ones that we might use to scan with to those that we might use to work, hold, or fabricate with. We're interested in this kind of reciprocal process between the data of bamboo and material resistance and kind of design application. and trying to use a generative system where if we know each pole, we can get the most out of it. On the left is the most recent machine we built, a 4-axis machine, bamboo. So here's just 4 examples from retooling bamboo. The one on the far right, you can see in the lab over here. It's a cast plaster and bamboo wall. The one next to it that's red was an early experiment. 2 former faculty that were also part of some of this research, Katie McDonald and Kyle Schumann, were very engaged in that project as well. And we were experimenting with how to tool bamboo in a way that would change its visual expression. We decided to paint it for 2 reasons. One is it really called out the kind of woodiness when we cut through it. The other was to help preserve it and to really allow one to see the form instead of just the material. Again, we're trying to kind of reboot this idea that bamboo is poor man's timber. The one next to that is a ceiling that's up in the faculty apartment, a canopy, designed and built by students in a couple of courses in COS, and then built this summer, as was that wall. And the one to the far left is the first larger expression of really trying to understand how we could use the generative process, and I'll explain that in a future slide. So we're also interested in how the research kind of leaves the lab, and so collaborating with a soon-to-be visiting scholar and a doctoral student here, we ran a course in Tehran, and they used the principles we're working with. They found local bamboo, they hacked a machine and built their own rotational device with an Arduino, and built this installation. So next, we're hoping to build some more of these reciprocal structures. And if you look at the images from the far top right, the top row, what we're doing there is we're simply trying to orient a joint along the middle of an internode of a pole, trying to have a kind of vernacular control over nodes and pattern, not thinking about mathematical pattern in a traditional kind of way, thinking more in a natural way about how we might control the kind of variability of bamboo versus the kind of very organized intent of a designer. In the far left, bottom left, we're looking at how we might so we're flopping the poles around. We're turning the poles into different positions. And then the far bottom right is what we've sort of come to, which is the idea that originally we thought, oh, you just have to worry about where the nodes are, but you still use linear measurements. Parts can all be uniform lengths. And then we realized, wait a minute, the bamboo has its own language. Can that be the first sort of seed of the way a pattern is formed? So now we're really focused on thinking in nodal measurements. So parts won't have a given length. They'll have a possible range of length, and we'll sort through a list of node sections, finding the best fit, letting the pattern, letting the human intent vary based on what the natural material wants to provide for us. And so that image on the left, we're going to build the end of the semester in a course, and it really uses that concept. And one of my collaborators, who I hope will be here by then, Hauptman, did the kind of design for that. So the next project is the one that I think has the most potential for, kind of impact in terms of carbon sequestration and in terms of the, kind of human-built environment. James Wolf, this collaborator I talked about, his image in the left, he cut a pole for me into a 4x4, and it worked once, and it didn't work the second time. And as an optimist, I came home only remembering that it worked. And so I set out to develop a panel system using the solid nature of a less solid but still rather solid species known as Tre Gai in Vietnam. The idea was, could we turn a line into a plane? Could we kind of convert the intelligence of biology that is a sort of, column into a surface? We thought about other materials that make planes. SIP is a pretty good one. So is CL2. We thought, where would this sit in context of those building systems? Would it be for North America? Would it not be for North America? So we've done a fair bit of development now. We're building a small installation next. Here's just a sampling of some of the things we're doing. So in the far left, we're looking at how to make interstitial kind of inline joints so we can straighten and grade thicknesses. The images in the second column, we're looking at what orientation the bamboo should be for cross-lamination, also what glues should we use. We're working with some chemists and biologists from UC San Diego who have developed biodegradable resins. And then the column that has one direction of lamination on the next sort of row, or the panel that looks like conventional framing. So we're really trying to look through many different parts of what we might call a new form of mass timber with bamboo. We've already done some testing, and it looks like panels that have poles through the middle the long way when we go to break them outperform all the other configurations, which in my mind reinforces the notion that you can convert a line to a plane. We're interested in how that might become generative and how you might put bamboo in certain places in the panels where it's most needed for a panel strength, but also how you might map that onto a building, very much in the same way that the bamboo pole itself as it grows. At the bottom, it's the most woody. In the middle, it has the highest ability to bend. At the top, it's the thinnest. This is because biology has made it that way so that it can bend in the wind. So next, we're going to build this little kind of installation. It's not truly necessarily an architectural installation, but it's an opportunity to force us to figure out joints and assembly and make an expression that other people can see, enjoy, and become part of the conversation. And that's happening in a course as we speak. Just a list of collaborators. Should also mention ICAT's support of 2 of these projects, which I mentioned before, one with a major seed, one with a minor seed. And the AIA Upjohn Award is how this work has been funded until now. And then I'd ask anyone that's interested to scan that QR code. We produced a video that was in the Venice Biennale that does a way better job kind of capturing the essence of all this work than I ever do when I give a talk. Thanks.
Thank you so much, Jonas.
Sure.
What a fascinating way to go. Anyway, I'm just loving bringing the physical characteristics of the natural object into the engineered space. I love it. What questions do we have? If you're online, be sure you put them in the questions list there. Coming your way. I'll hold it.
Thanks, that was a great talk. I was wondering, do you know if there's any research in like bioengineering in bamboo? Are any people working on that?
Can you be more specific?
Like genetic modification in bamboo, for instance?
I believe there is. I don't know much about it, but there's also, there's definitely more than one community. Some of the communities that work with bamboo are very concerned with, a monoculture and just concerned with trying to be restorative and use natural processes. But there's definitely been some work, as far as I know, mostly in the private sector, and there's also some work that I've seen in India. But I don't know much about it. Yeah.
Who else has a question? Holly, I'm going to check your computer. Okay. I'll come. Oh, let me.
So this is just a question from Ben to Jonas. So does that mean we can't grow our chair anymore?
It does, yeah. So what I determined was that yes, we can totally influence its growth. And in fact, I met a family in Kyoto that has been growing bamboo for 500 years, and they grow it square. There's a part of a tea house, a Japanese tea house that, and I don't know this history at all, but they grow it square for this tea house. And when it comes out of the mold, which is 12 feet tall, it takes this incredible curve and then shoots up again, even though it stays square in section. The trouble is that bamboo grows from a rhizome, so when they grow those bamboo poles that way, they have to be very selective. They can't grow the whole patch. So when we're growing bamboo the way that we're talking about, the bamboo relies on the previous year's growth. The foliage is what feeds the bamboo, right? So in other words, you really can't make them all different. You might be able to make a big chunk of them sort of the same, but not in the way that we imagined.
Can you talk about how you got started in
Sure.
bamboo research?
Yeah, so when I came to tech, I was asked to teach materials and process, and that I'm well suited to. I'm trained as a craftsman and a sculptor. I've taught architecture and design, and I've always been focused on material innovation, invention, creativity. And when I was thinking about how to structure this course, and thinking a little bit about sustainability, but also just about how boring I think it is just to talk about materials that, one, that I already know, or two, that the students will probably already know a lot about. I started thinking about a project I did in California about 20 years ago now, and I took palm from the LA dump, palm fronds, and made composites with them for furniture prototypes. And as I started researching palm, I remembered that I had footnoted an interest in bamboo. This is before the flooring industry even started, really. But I never did anything with it. So I started researching it again for a lecture and was like, wow, this is cool stuff. And actually, that's the day I went and talked to Ben about growing crazy bamboo. So it wasn't really very preconceived. It was suddenly I realized how interesting and challenging it was. And to be honest, I didn't think it was as challenging as it really is. It's way harder than I thought.
We do have a question online from David. As you know, as many of you may know, bamboo is quite invasive, or can be quite invasive in North America. Can you talk about how we can manage the invasiveness as a crop?
Yeah, so first off, I think ornamental bamboo, has to be very well managed. I think that there are some species that could be cultivated for timber in the United States, but I think that the market for timber, and also the amount of timber that's already available, I don't think that bamboo is an immediate slam dunk. There's one company left that's trying. They're doing some really cool stuff. They're called Bamcor. But recently, 2 other companies have failed to kind of stay in the market with kind of structural bamboo products. We're really thinking about Latin America. We're thinking about the belt where bamboo grows natively. So in a way, I don't have a strong opinion about whether we should grow it in the States or not. What I would say, though, is I'm not convinced yet that there's an economic model, and I haven't studied it.
So we shouldn't all go plant bamboo in our backyard.
Well, I have it in a pot.
Do what?
I have it in a pot still. My wife
Okay, in a pot is good.
My wife hasn't let me put it in the ground yet, but I would. Just needs a barrier, you know.
What other questions do we have?
Hi, Jonas.
Hey.
Could you talk about how the adhesive in the laminated bamboo contributes to both, or impacts, 1, sustainability, and 2, strength of the structure?
Sure. So we don't know everything yet, but we've done, there's many ways to test adhesives and how they bond to materials. And I'm not a material scientist, so I will definitely butcher this. But in a simple sense, the most primitive test that you do is called a peel test. And you basically take 2 small samples, you glue them together in basically a lap, and you pull on them. And so we studied several glues. We didn't study epoxy because we're very confident it will work, but that it would be a nuisance and also not particularly environmentally responsible. We studied typical wood glue, we studied polyurethane glues, and we studied this algae adhesive from UC San Diego. And the typical wood glue and the algae did better than anything else. Oh, and we used urea formaldehyde as well, which is the typical structural adhesive used in industry for wood or for bamboo. So we're using an off-the-shelf wood glue right now. Our goal is to eventually use a polyurethane that's biodegradable. We don't yet know whether or not the cost of that will bear out or not. It also isn't fire rated yet, which is another problem. But we're hopeful that the polyurethane will work. But even if it didn't, if you compare, here's the alternatives. A core that is of green material with a little bit, let's say, of non-biodegradable plastic in it, right? If you compare that, the damage that would do to any conventional construction, even, let's say, wood construction with building wrap, we're using way less polymer than you would even in that. But let's go a step further and imagine it's compared to concrete block and steel. the amount of embodied energy, the amount of damage we would do in this system is just significantly less by far. So we're hopeful to have a really holistic solution. That's why we're also trying to grow mushroom roots. That's why we're using the algae. But we're trying to kind of parallel path where we continue to work on the bigger problem, which is the way to kind of build the mechanical composite of elements. But we're definitely aware that we want to make the kind of greenest solution that we can. Unlike timber, where you could dowel laminate it and have no glue, bamboo's taxonomy would just fall apart if you put holes through it like that.
Okay, well, we're at time today, so thank you so much for being here this morning. Thank you if you came online as well. Jonas, appreciate your time and energy this
pleasure.
morning. Anyway, I'm so excited I'm ready to go build something out of bamboo now. We'll be back here next week, same time, same place. And we'll see you then. Thanks. And we have donuts.